Good morning, everyone. This is Mr. Baldwin here, going over chemical foundations, which is going to be our topic for our Unit 1. I'm going to take some time and sort of go through a few things. Some of it will be reviewed, so I may move through it kind of quickly, but if that is the case, you can always stop, pause, rewind, and go over it until you have it. Now, our goal for this unit or for this section of the video is want to look at how we can how I can prepare you to be able to explain how the steps of the scientific method are used and adapted in development of the modern atomic model, going all the way through to Schrodinger. Now, in terms of what we're going to cover here in this PowerPoint, it is only up till we get to Rutherford. So we're still going to talk about Schrodinger, we're still going to talk about Bohr, but we're going to save them for a little bit later once we get into atomic structure and periodicity, where we have to talk about, the energy levels and all these different things. Now, when we go around on the regular basis, we tend to make observations. These observations can be very detailed when noticing what someone's wearing, the colors, the patterns, different things like that, or it can be very general. Or I noticed that a lot of students at the school prefer a certain type of beverage or a certain type of food, or just like to sit outside rather than sitting inside. All of this is allowing us to be able to collect data. Now, from this, many times we will form a hypothesis. We have a thought that goes to our heads. Based on the information that I'm seeing, I think this is why. So if everyone's sitting outside, you could possibly make the hypothesis that the students prefer to sit outside because inside the cafeteria is too hot or too crowded or different things like that. These are all things you can do experiments to test to see if this hypothesis holds true. Now, the thing about any hypothesis, about any in scientific questioning and process, usually it's going to be repeated a couple of times, sometimes several hundred times. Think about things such as Formula 409. He actually tried it 409 times before he got it right. So with this information, we want to continue to refine and process and move towards our desired result. Now, in a regular scientific setting, there are a couple of routes that we can take. Yes, we have to make our observation, our hypothesis, and our experiment. Those are key. But from that point, we can move into one of two areas, especially when it comes to scientific exploration, to understand things that we don't yet see or understand, or even things that we do see, but we still don't fully understand why and how they happen. One, if we're trying to propose the how or why something happens, we may move into a mode of a model or a theory. This will be a statement of belief of why something happens that will be refined and sort of honed until it gets to the point where it is a solid, supported theory. Now, even in all of this, it still cannot be proven. That's one of the things you want to make sure. A theory can never be proven, it can only be supported. Now, on the other side, we have a scientific law or a natural law. These are things that we observe every day. We may have a lot of math to try to understand it, but it's more of the what happens. In the case of this pencil, if I throw it up, I know that it's going to come crashing down to the earth. I don't have to guess. I don't have to say, well, maybe this time it might be different. With that in mind, we'll move into the next step, looking at our atomic model and seeing how we progress. So now, where do we go from? Now, when we have a model set, this is going to be, or it's going to carry a set of assumptions that are trying to explain, again, some behavior of matter, like we talked about the atomic model. Now, this is going to change and it's going to develop in ways a long way away, sometimes from where it originally started. But again, it's just a set of assumptions. It's what we know based on what we can actually test and see. There are going to be some things that we find that are outside. We're going to see that this model, the models that we use will change. They'll develop into something greater, more specific access of information or description of information. So, do a quick review of the men and their experiments that gave us our current understanding of the atom, where it came from and how it's sort of set. Now, we start off with our discussion with Democritus. Now, around 400 BC, he was a philosopher who first postulated that this matter, this stuff that we're all made of, had a point where we couldn't break it down any further. Now, he named this substance atomos, which of course is where we get our idea for the name atom. But what was the problem with his information? All he did was think about it. He had no experiment, no results, therefore he got no credit. Even in terms of the philosophers of his day, he was usually pushed to the side. Many of his contemporaries, such as Aristotle, Socrates, these great men of thinking and of learning, they carried a little bit more weight. Now, in our class, we do not want to go the route of being a philosopher and just having this idea. We want to have something that we can physically test, something that we can look at and say, okay, we have proof that this exists or this behaves this way because of whatever phenomenon that we have observed. Now, about 2,000, somewhere around 2,000 years later, or a little less than that, we come to our friend John Dalton, who actually studied a lot more meteorology. While he was studying the effects of atmospheric pressure, he came up with Dalton's law of partial pressures, which we'll talk about in our gas laws unit, chapter 5 of your text. But also, he did a lot of extensive experiment with gases where he actually found that this thing that Democritus was talking about before, there actually is proof that we have these individual particles that can only go so far. One of the things that we observe all the time with gas is if I have a plastic bottle and it's closed, I can only close it and wrap it up and bind it up so tight before it either the top goes flying off or it bursts on its own. Why? Because you have these atoms in there and they're taking up this space and they're bouncing around. This is what he used as he started to develop what we now call the atomic theory, the first draft, or we'll say, of the atomic theory. Now, take a moment, look in your textbook, read through the information about the original atomic theory, because in a few moments I'm going to ask you to compare it to the modern atomic theory. What's changed? What's different? What stayed the same? How can we account for, or what is our evidence that these things have changed? You want to use your text, and we'll talk about that a little bit more in class. So again, Dalton challenge, what parts of the Dalton's atomic theory have been altered from their original state? And we have here a picture of his model, basically just a ball. So take a few moments if you want to pause it right here, and I will come back in just a moment and we'll proceed from here. All right, now from Dalton, we continue on just a few years, and now we end up with our good buddy J.J. Thompson. Now, J.J. Thompson was from England, and his main experiment was what was called the cathode ray tube experiment. Now, in this experiment, basically what happened is, before he would run, as you see in the picture here to the left, you see that they have a tube that's filled with some sort of a gas, and then electricity is run through that tube. As you see from the picture, the current goes straight through. Now, because of these findings, scientists of that time thought that, okay, there's no charge to the actual gas inside because the electricity just goes straight through. There's no deviation. Now, J.J. Thompson in his studies found that, okay, what happens if I put a charged plate, or put two charged plates around the cathode ray tube? In one case, they actually put a magnetic bar. And what they observed is that the electricity bent away from the negatively charged plate. And this was most dramatic because you can see it right here on the side. Now, using our logic and our understanding of electromagnetic radiation and fields and attractions, we know that opposites attract and like charges repel. Based on these findings, based on what he observed and what has been proven over and over, we have negative charge. We have to have a negative charge because it bends away from the negatively charged plate. Now, from this, Thompson is able to now look and say, okay, well, Dalton had it wrong. The atom isn't indivisible. We actually found that it is divisible. And so this is where we come up with the plum pudding model. This is what you usually hear referred to when you're talking about J.J. Thompson. And basically the idea was that I have these negatively charged electrons, at the time he actually called them corpuscles, floating around in a sea of positive charges. So the positive charge is sort of like a jelly and the electrons are actually like just the raisins. And this is the reason they call it the plum pudding model. It's a popular dish in England. Now, for all of these things, we continue to build and say, okay, we've made great advances, but there's still somewhere to go. We still have some room to grow. So we're going to fast forward a little bit to the early 1900s, and now we're going to come to Ernest Rutherford. Now, he was an English physicist, so same country, but maybe working with a different field. The great thing that I love about Ernest Rutherford's story is he originally was not trying to set out to prove or change the model of the atom. But through his experiment, through his studies, he actually found that there was something that was different than what was known at that time. Now, his gold foil experiment was basically he shot alpha particles, which are basically helium nuclei, at a thin piece of gold foil. This thin piece of gold foil is about 200 atoms thick, so it's very, very thin. And when he shot it at this gold foil, his expectation is that they would go straight through, no problem. If you look at the diagram here to the right, you're noticing that you have several of them that go right on through without a problem. But you just have just a few that either deviate or bounce completely back, going towards where they came from. What they did is, or how Rutherford set it up is, he actually set it up with a little detecting screen. And it wasn't him who originally looked at it and said, oh, wow, this is happening. He saw it and said, you know, it's not statistically significant, the amount of particles that are bouncing back. But as he continued to study, and his lab assistants continued to study, they found that this was happening more and more often. Again, revisiting Coulomb's law and the law of electromagnetic force, he looked at it and said, okay, well, if these are positively charged particles that I'm shooting at this foil and they're bouncing back, that means they have to be hitting something positive, but also they have to be hitting something that is dense, something that is solid. That being the case, we were able to change, again, the idea that we had for this model. Now, in this time, I don't think they necessarily drew the picture and said, okay, this is the model of the atom. But I want you to take the information that we've covered thus far, and I want you to make a decision. I want you to choose which of these atoms is the current model, at least up to the time of Ernest Rutherford. Which one is the model that was used after Rutherford's experiment, based on the information that we have thus far? Go ahead and write this and draw a picture of the one that you choose in your notes. And when you come into class, we'll have a little discussion and see what everybody's finding and what's sort of going on in your minds, and see how we can sort of tweak and make sure everything is solid. We're going to end it there for right now. This is the end of the first video. Hopefully, if you need to rewind, you can do that, or pause, or whatever you need to do. I look forward to seeing you in class. Thank you very much, and have a great day.